Hello viewers, welcome to my channel KK Concepts of Electrical Engineering. Magnetic field intensity at a point on the axis of a circular loop. Let us consider a circular current loop of radius r0 carrying a direct current of I in clockwise direction. The point P is on the axis at a distance x. Consider a differential element dl1 at the top at one side and I dl2 at the bottom. Then the distance between the point P and the differential element is a small r. This dl1 equals to dl2. Point P, let this be x-axis and this is our y-axis, and this is dh2 and this is dh1, and the angle between these two is 90 and these two is the 90. This angle is alpha, this angle is alpha. From BIOT-SARVART law, dh1 is the magnetic field intensity due to dl1, which equals to I dl1 sin theta divided by 4 pi small r square. Angle is 90 degrees. This value is I dl1 divided by 4 pi r square is dh1. Similarly, dh2 is the magnetic field intensity due to dl2 on point P, that is given by I dl2 divided by 4 pi r square sin theta. Then theta is 90 degrees here also, so this is I dl1 divided by 4 pi r square. Right hand screw rule, this is the direction of dh2 and dh1. dh1 and dh2 are divided into two components, dh1 into x component and y component, and dh2 also we can divide into two components, x and y. So this one and this one is the x components and vertical ones are y components, but whereas this component is upwards, this component is downwards, so y components of dh1 dh2 gets cancelled and x components of dh1 dh2 will be added up. X component of dh1 is equals to dh1 cos alpha and dh2 is dh2 cos alpha. So from the figure where cos alpha is equals to is the alpha, so capital R by small r. Now when you substitute this, then dh1 r by small r, x component of dh2 is equals to dh2 r by small r. Components of dh1 dh2 add up, then dh is given by dh1 r by small r plus dh2 capital R by small r. Then dh1 we know, that is I dl1 divided by 4 pi r square multiplied by r by small r plus I dl2 divided by 4 pi r square capital R by small r. Then dh is given by, dh is the magnetic field intensity due to dl1 and dl2, I r divided by 4 pi r cube of dl1 plus dl2. Total magnetic field intensity, that is H, is equal to integral dH. H is equal to integral 0 to 2 pi r dH. H equals to IR divided by 4 pi r cube integral dl1 is the half of the part, so 0 to pi r plus another half of the part, that is 0 to pi r lower circle dl2. Since the dl1 equals to dl2, the 2 can be replaced with the dl, then this will be equals to IR divided by 4 pi r cube of integral dl 2 times 0 to pi r. This equals to 2 times, then IR by 2 pi r cube dl. If you integrate, then L you are going to get from 0 to pi r. This equals to IR divided by 2 pi r cube pi r pi h equals to I r square divided by 2 small r cube amperes per meter. Now from the figure, r square equals to capital R square plus x square. This formula will become h equals to I r square divided by 2 r square plus x square 3 by 2 ampere per meter, acting along the x-axis. In vector form, then h equals to I r square divided by 2 r square plus x square 3 by 2 ur in amperes per meter. Vector form. The flux density B equals to mu naught H in air. Then B equals to mu naught I r square divided by 2 into r square plus x square whole to the power of 3 by 2 ur Weber per meter square. In this formula, when x tends to 0, which is nothing but the point P comes to center of the circle, then h is given by I r square divided by 2 r square whole to the power of 3 by 2, which equals to I by 2r amps per meter. In vector form, then h equals to I by 2r ur amperes per meter. Flux density is equals to mu naught I by 2r ur Weber per meter square. This is the magnetic field intensity at the center of the circle, and this is flux density at the center of the circle, which are similar to our previous video.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.